Okay, I'll just take one favor to so we got one problem on. Can you pass that for me, please?
All right, folks, if we could dial in. We have a lot of material to get through. So you have a test on Friday. It's not, hopefully, one of the more difficult tests in terms of complex concepts and things like that, but there are a number of things that are going to show up on that test. So we've got a lot of little bits of review topics for you. When you look at your review sheet, you'll see that there's a number of terms. We've got concentrations, molarity and dilutions, and solutions, stoichiometry, acids and bases, conjugates, and titrations, and pH scale. So I'm going to go as quickly as I can, or as quickly as you let me. I don't want it to take longer than it needs to. If you're all good with this stuff, but I'm not going to stop unless you ask questions. Certainly I'll be asking periodically if you have questions, but please, if there's something that doesn't make sense or it needs a little clarification, don't be shy. Otherwise, we'll just keep rolling. So we're going to start with terms. There's a whole bunch of them. We're going to hit the first few of them. These should be reviewed from your lab classes on either Mondays or Fridays for the most part. And they may be worded the same, they may be worded different, but we'll zip through them and see if you need any extra clarification on those. The solute is the stuff that gets dissolved in a solution. The solvent is the substance that does the dissolving. A lot of times you'll have a solid as your solute. Mr. Gussie or Mr. Neubauer used the Kool-Aid. Mr. Gussie used the Kool-Aid analogy. You take that Kool-Aid powder, that's a solid. You put it in your water, that's a liquid. So your solute would be the Kool-Aid powder, the solvent would be the water, and the result is your solution. If you got two liquids, the solute and the solvent is determined by which one has the smaller and larger volume. So the solute is the smaller volume, and the solvent is the larger volume. And everything that we have worked with, our acids, our bases, so the NaOH, the HCl, all of our solutions in lab have been aqueous, meaning that they have been dissolved in water. And so in an aqueous solution, something dissolved in water, water is always going to be your solvent. Too fast? Right away. Right away, too fast. Bless you. Something is soluble, it's able to be dissolved. If something is insoluble, it's not able to be dissolved. Some substances might be soluble in one solvent and insoluble in a different solvent. We've had some experience with that from lab. It's been at least a couple of months now, but when we were investigating ionic compounds and molecular compounds, we were looking at solubilities of those, and we tried to dissolve salt in water. Worked like $1,000,000 because salt is soluble in water, but it was not soluble in alcohol, so it wouldn't dissolve in the alcohol. In general, things are like dissolves like, so polar compounds are going to dissolve in polar solvents, nonpolar in nonpolar solvents. That's not on the quiz or the test. The solubility is a measure of how much of a solute can dissolve in a given solvent. So it's going to have the units of grams in terms of how much can we dissolve per volume or mass of our solvent. So it's going to be grams per gram or grams per milliliter, grams per liter, something like that. And we'll see that on our solubility tables in just a moment. You've got a couple examples of those on your sheet. Miscible and immiscible refer to the mixing of liquids. If two liquids are miscible, then they will mix. Water and alcohol. If the liquids are immiscible, then they won't mix. You can certainly stir them up, shake them up, but you'll be able to see that they aren't a homogeneous mixture. Gas and water, for example, if you get water in your gas tank of your car, your lawnmower, you can usually see, at least in your lawnmower, if it's push mower, look in the gas tank and you see little spheres, little droplets of water in the gas tank. It's not good. You don't want that. Oil and vinegar. Your oil and vinegar salad dressing, you shake it up. It mixes up, but quickly separates. You can see the bubbles where the oil and the vinegar are not truly mixing. So those are immiscible. Here's our first solubility curve. That's the top left on your note sheet. Pretty generic. It's got two compounds on it. We've got sugar and salt. You can see that salt is pretty constant. Doesn't change much with temperature. Sugar, the solubility of sugar changes quite a bit as the temperature increases. What we want to focus on is below the curve, on the curve, and above the curve for saturated, unsaturated, or supersaturated. So if we have a saturated solution, well, actually, let's start with unsaturated. Unsaturated, anything below the curve means that we can still dissolve more of that solute in the solvent. We can still dissolve more. If it's saturated, then we've dissolved as much as we can. And if you add more, it is just going to sink to the bottom. And you'll have your sugary sludge of Gatorade or Kool-Aid if you try to put too much in the jug or in your bottle. And then supersaturated solutions are where we have dissolved more than what you typically can, and it usually requires special conditions. You may try heating the substance up. You can see that as the temperature increases at 100 degrees, we can dissolve a lot more sugar than we can at, say, 20 degrees at room temperature. So we may heat it up and dissolve, say, 350 grams of sugar in our solution, which is unsaturated, at 100 degrees. And then if we slowly cool it down to 20 degrees, if we keep all that sugar in solution as it cools, then we'd have a supersaturated solution. So it's generally done by heating it up and then saturating it and then trying to cool it down and keep that solute in solution. Easier with some substances than others. Sodium acetate is the one that we demonstrated in class. That's a very relatively easy one to do. Our other solubility curve, just want to give you a quick refresher on how to read this and what kind of information it gives you. On the vertical axis, it tells you what your solvent is. So we've got 100 grams of water. With water, 1 gram is equal to 1 milliliter. So you can directly convert between those two units. So whether you're talking about mass or volume of water, the numerical value is going to be the same. And we got a whole slew of different compounds here at different temperatures. So on the next slide, I've got 3 questions that I would, and they're not written on your note sheet, but if you would take a moment to use the solubility curve on your note sheet to try and answer each of these 3 questions. It'll take 30 seconds or a minute to do that, and then we'll follow up and make sure that we're all up to speed on interpreting our solubility charts. So the first one asks, what's the solubility of potassium chloride at 70 degrees Celsius? Then what's the temperature at which potassium chlorate has a solubility of 20 grams per 100 milliliters of water? And then finally, at what temperature do potassium chlorate and potassium chloride have the same solubility in water? None of these 3 questions require any calculations on the review sheets. On the test, we may have a question that requires you to use a proportion on the review sheet that you already completed. I know there were some questions about how much can you dissolve in, say, 300 grams of water. So for that, you would look at how much you can dissolve in 100 grams and then just multiply it by 3. Done? That gets old in a hurry, huh? All right, so Bailey, what do you got for the first one? Solubility of potassium chloride at 70 degrees.
About 48.
Perfect, about 48. That's what I got. Nice. M, what do you got for the temperature at which potassium chloride has a solubility of 20 grams per 100 mils? You're both M. It's fine. I got about 50, which is about 48 or 49, so it's all good. And finally, at what temperature is the solubility of those 2 substances equal? Who wants a piece of that action? Robert? About 94. So if we go back to the chart here, for the first one, we're looking for KCl. That's this guy. And 70 degrees. So we're right there, just a little bit below 50. The second one was potassium chlorate at 20 grams per 100, and that's just about 50 degrees. And then for the last one, we're looking at where the potassium chloride and potassium chlorate curves intersect. They both have the same solubility at that point, which is a little above 90, 94, 95 degrees. Good. Alrighty, concentrations. Generic definition for concentration is how much solute we can dissolve in the solvent. How much solute can we dissolve in our solvent, in a given amount of solvent? More specifically, we've been using molar concentrations or molarity, which is defined in terms of the moles of the solute. or 1 liter of the solvent. Mr. Gussie introduced our little molarity triangle a couple of weeks ago. You're going to see that guy several times today. In the event you don't remember how to use our molarity triangle, you're going to cover up what you're hunting for. So if we're looking for moles, we cover that up. We multiply molarity times the volume in liters. If you're looking for liters, it's going to be the number of moles divided by the molarity. And of course, the molarity is moles over liters. Works like $1,000,000. So let's do one. What's the molarity of a 1 liter solution containing 9.0 grams of HCl? Give it a little pressure on our molarity triangle. We want molarity, so we need moles over liters. We don't have moles. We've got a liter, but we don't have moles, we have grams. What to do, what to do? So at this point, I'm not really telling you what to do because I'm thinking you probably know what to do. We need to convert our grams into moles and then apply that to our molarity triangle. So we're going to start with 9 grams of the HCl. Refer to the periodic table for the molar mass, HCl 34.5 and 1. Right, 35.5 and 1 gives us 36.5 for the molar weight, molar mass, and that gives us 0.25 moles of the HCl. So that's how much stuff we have to dissolve, and the fact that we're dissolving it into 1 liter tells you that guy in your head. 0.25 divided by 1, 0.25 molar. That's easy, right? All right. Okay, slow me down if you need to. Let's do another one. How many grams of NaCl are required to prepare 350 mils of a 2 molar solution? So before we were given grams and wanted to find molarity, now we're given molarity and we need to find grams. Many of you, most of you I hope, are working on it or already solved it. If you're not doing this because it's too easy, well, that's good. If you're not doing it because it's too hard, you're going to have trouble. So we're going to start with the molarity and the volume. 2 molar and 0.35 liters. We were given milliliters. I didn't show the conversion there, but there's 1,000 milliliters in a liter. So to convert from milliliters to liters, we're going to move our decimal point 3 positions, divide by 1,000. So molarity times liters gives us moles. So we got 0.70 moles, and it's just a case of finding out how many grams is 0.70 moles. Molar mass of salt, sodium chloride 58.4, gives us 40.9 grams. Once you've got that, if you would take just a moment to look at your solubility table, the top one that's got the solubility of salt in water is a 2 molar solution of salt in water realistic? Would that be supersaturated, almost saturated, or comfortably unsaturated? Sorry? I'm asking again, if 41 grams in 350 mils is a realistic amount, so is it realistic to get a 2 molar solution of salt water? How many grams of salt can you dissolve in 100 grams of water? And it's pretty consistent, pretty independent of temperature. Brooke, what do you got? How many grams of salt in 100 grams of water? About 40. And that's just in 100 grams. We got 350 milliliters, which is 350 grams of water. So we could dissolve about 3.5 times that much. So it's very reasonable. Unsaturated. Dilutions of solutions. Now that we've got our 2 molar salt solution, what if we want it to be not so salty? So we're going to dilute it from, say, 2 molar to 0.5 molar, or 2 molar to 1 molar. Is the number of moles present in the solution going to change? Well, certainly it could, but if we're going to keep our whole sample and dilute it, then the amount of salt is going to stay the same. The only thing that's going to change as the molarity decreases is the volume is going to increase. So let's take a peek at that. So here's how we do that. We add solvent to lower the solution. In this case, we'd be adding more water. So if this is our salt water, initially, we've got 18 particles of salt in there, dissolved in a relatively small amount of water. If we double the amount of water, we still have the same amount of salt floating around. It's just not as salty or not as concentrated because there's a lot less salt per volume. So, for our dilutions, and Mr. Neubauer introduced this equation last week, M1V1 equals M2V2. This represents the molarity of our concentrated, our starting solution, and the volume of our starting solution. This would represent the molarity of our diluted solution and the volume of our diluted solution. So if we know 3 of them, obviously we can solve for the 4th. Let's do that again with sodium chloride. If we got 0.2 molar, let's say that this guy, this concentrated one, is 0.20 molar, and we want to dilute it to 500 milliliters of 0.01 molar. Actually 0.001 molar. So we're going to dilute it a lot. It's going to go from 0.2 to 0.001. I want to find out how much of this concentrated stuff we need to use to make 500 mils of the diluted stuff. And this one you don't have a spot for. The next one you will, when we dilute the sulfuric acid. But we're simply going to take this equation and rearrange it. We're solving for our concentrated volume. So we're going to have M2V2 over M1. Our molarities will cancel and we'll be left with a new volume, which, if you work through that one already, it's going to be 500 times 0.001 divided by 0.2, which should give you 0.2 or 2.5 milliliters. If you used 0.500 as your volume, then your answer would be 0.0025 liters. That's good. Easy. This stuff's just flying by, right? Yeah. Giddy up. Let's do another one. Using the same equation. Want to find out how we could make a solution of 800 milliliters of sulfuric acid, H2SO4, that's going to have a molarity of 2 moles per liter. And we're going to start with a 6 molar solution. So 6 molar is our concentrated stuff. We need to know how much of the concentrated stuff we need to mix with water to form 800 milliliters of the diluted. It's going to be exactly the same form of the equation that we just used. So hopefully, Ryan, your work looks something like this, where we rearranged our M1 V1 equation to solve for V1. .26 liters is the volume of the 6 molar solution that we need. So if you're going to make that solution, we'd take an 800 milliliter volumetric flask, fill it with halfway or so with distilled water, knowing that we need to add 260 mils of the concentrated acid, concentrated solution, and then we would fill it the rest of the way with water. Any questions on that? Easy peasy, let's keep going. Titrations. Only going to have one or two slides on this. We'll come back to titrations when we talk about acids in a few minutes. But a titration is, and we can just read this verbatim, chemical analysis used to determine the concentration of a solution. That's what we did in the lab. We took a known concentration of our sodium hydroxide. We measured a known volume of it as we titrated it into our known volume of hydrochloric acid. And from that, we were able to calculate what the molarity of that hydrochloric acid was. We'll come back, we'll revisit titration. Am I going to that? No, go. Don't be shy. Good idea. All right, solution stoichiometry, here we go. I'll go faster if I'm not keeping you busy. Solution stoichiometry, we got really two choices or two types of problems. Generally, you're either going to use the molarity equation to figure out how many moles of something you have to react, and then you'll use your stoichiometry map to figure out how many grams or moles of a substance you need. Or you go the other way. Or we're either going to use our stoich map and then our molarity equation, or molarity equation then our stoichiometry map. So here we go. One example of a solution stoichiometry question. What's the minimum volume of 1.2 molar HCl required to dissolve 8.0 grams of calcium carbonate? First thing you're going to want to do is jot down the balanced chemical equation. Well, you don't have to do that because I've already done that for you. But the next thing I would do is write down what's given below those particular items. So 1.2 molar HCl, 1.2. 8 grams of calcium carbonate, 8 grams of calcium carbonate. That's going to help us figure out what our path is to get from where we are with this stuff to what volume of HCl we need. In order to figure out the volume of the HCl that we need for a given molarity, we need to know how many moles of HCl. And I didn't put the little triangle up there this time. But if you look at your molarity triangle, your liters of solution are going to be equal to moles over molarity. And we've known how to get from moles of a reactant to moles of the other reactant for quite some time. So that's going to be our first step. Go from grams of calcium carbonate to moles of calcium carbonate to moles of hydrochloric acid. So you want to make sure that you have your equation balanced correctly, or want to double check to make sure that it is balanced if it's given to you. So when we plug and chug through this, you should find that you get 0.16 moles of HCl. Then we're going to use our molarity equation to figure out what volume we need. Because again, we have the molarity, we now have the moles. Molarity is moles over liters, so liters are going to be moles over molarity. We got 0.16 moles, 1.2 molar. Remember, the units on the molarity are moles per liter, so really we have moles divided by moles over liters. So our moles are going to cancel. Our moles over liters, bottom of the bottom, comes to the top. We'll be left with units of just liters, which is what we're looking for. 0.133 liters, that's your guy. Kill it. Is he? What?
I just said no.
Any questions on how we got from the start to the finish of this guy? Perfect. Acids and bases. I wouldn't write all this down. I got something else for you to write down. It's just some nice to know stuff. But if you've ever eaten soap, tasted soap, had somebody hold your mouth open and wash it with soap, you notice that it tastes very bitter. Not good. Acids are sour, like lemon, lime, citric acid. Very sour. Bases are tend to be slippery, as you know with soap. Slippery, if you've ever had bleach or bleach water, felt that. It's got definitely a slippery, slippy consistency. Well, here's what we're worried about. Here's how we're going to define acids. A Bronsted acid, or for our purposes, that's how we're just going to call that an acid, is a proton donor. A Bronsted base is a proton acceptor. And this should look familiar from last week. How many times, Dustin?
Oh, it's so bad.
2 times? And then hopefully you recall that the other terms that we talked about, or Mr. Neubauer talked about, were conjugates. What's the conjugate acid? What's the conjugate base? So these first two, the acid and the base, in your acid-base reaction, are going to be your reactants. This is what you start with, an acid and a base. When they mix, react, you're going to end up with a conjugate acid and a conjugate base. And there's 2 of those provided for you on the back of the sheet that we'll walk through. And here they are. So we want to label each of these as either acid, base, conjugate base. So if we look at our chemical equation, we got HCl plus H2O. Both of those have hydrogen. We're looking for the one, which of these gives up the hydrogen. So if we compare what our reactants look like to what our products look like, we'll see that we've got HCl as one of our reactants. We've got just Cl, chlorine ion, as our product. So that guy lost his hydrogen or donated. That's going to make HCl your hydrogen donor, and therefore your acid. And H2O is your base. Where did the hydrogen go? Hydrogens go to the conjugate acid. So the H2O gained a hydrogen and now became H3O plus, and again chlorine, the HCl lost its hydrogen, so now we just have the chlorine ion. So what used to be the acid is our conjugate base, and what used to be the base is our conjugate acid. Next guy, NH3, H2O. Who donates the hydrogen? The NH3 or the H2O? The H2O. You can see that over here, H2O becomes OH minus, so there's not 2 H's anymore. And we've gone from 3 hydrogen to 4 hydrogen. So the water in this case is our donor. So water can be either an acid or a base. And our hydrogen acceptor, our base, is the NH3. Our conjugates, what used to be the acid, becomes the base. Acid becomes conjugate base. Base becomes conjugate acid. So who gained the hydrogen? That's going to be our conjugate acid. Who lost it? He's our conjugate base. Got 3 compounds here. Bases, acids. What about this guy? Marcus, what do you think? HBr? Hydrogen bromide? Likely a donor or an acceptor? It's a donor. very much like HCl. The hydrogen compounds with our halogens are many of our strong acids. So that's going to be an acid because it's going to give up that hydrogen. How about NO2? NO2 minus. Izzy, is this going to give up a hydrogen? How do you know? That's very good. You can't give up what you don't have, so it can't be an acid. It's going to be a base. And then finally, water, we just saw, can go either way. Sometimes it can act as a base. Sometimes it can act as an acid. So it can either act as a base and accept a proton, become H3O plus, or it can give it up and become OH minus. Here's our pH scale. You got a copy of this at the bottom of your page on the back. Much clearer than probably what this is. All of these exponents of the hydrogen concentrations are negative exponents. It's not really clear. It's a little more clear on your sheet. But what I wanted to point out to you is, or remind you, is what you already know, that pH 7 is neutral, and the concentration of the hydrogen ions at pH 7 is 10 to the negative 7, which is not a lot. 10 to the negative 7 is a small number. But that tells you what the concentration of the hydrogen ion is. When pH is 6, the concentration is now 10 to the negative 6. Ryan, is 10 to the negative 6 bigger or smaller than 10 to the negative 7? Bigger. Bigger. That means there's more hydrogen. How much more? 10 times more. pH 5 has a concentration of 10 to the negative 5, which is 10 times as much hydrogen ions as pH 6. So every 1 unit change on the pH scale is 10 times as much acid, or 10 times as acidic as the number above it. Come back to that guy in just a moment. First we'll talk about titrations just a little bit. We already have a working definition for titration. Indicators and equivalence point. The indicator that we used in our lab, anybody remember what the name of that indicator was? Phenolphthalein. That's the one that turned pink. When? Well, it turns pink when you reach the equivalence point, or when the concentration of the hydrogen and the hydroxide ions are equal. So again, in a titration, we're doing a very careful, trying to do a highly precise dilution to try and identify the concentration of an unknown solution. Here's a sample problem. In this problem, we've got what's wrong? Yeah. You have a couple of options if I'm going too fast. You can either go, or you could raise your hand and say, that's just, and there's more than that. You do this. You do this. How are we doing now? Alrighty, 0.263 gram sample of sodium carbonate requires 28.35 mils of HCl to reach the equivalence point. In other words, to neutralize, and we want to find what the molarity of the HCl is. So, what do we got? We got 0.263 grams, we know that. So write that under your sodium carbonate. And what are we hunting for? We're hunting for the molarity of the HCl. As we've done with our other solution stoichiometry problems, we are going to figure out how many moles of HCl are required to react with this amount of sodium carbonate. And once we figure out how many moles for this given volume, the molarity is practically going to solve itself. So we're starting with 0.263 grams. The molar mass of your sodium carbonate is 106 grams per mole. If we stop there, that would tell us how many moles of sodium carbonate we have. We want moles of HCl, and there's 2 moles of HCl for every 1 mole of sodium carbonate. Bing, bang, and boom. So we got about 5 thousandths of a mole. And that's diluted in 28.35 mils. So we use our molarity triangle for that. We know moles, we know liters. We'll just divide our moles by our liters and get our molarity. And again, I did not show the calculation or the conversion from milliliters to liters. We're dividing by 1,000. We're moving the decimal point 3 positions to the left. Holy buckets. Okay. Last couple of slides are going to go fast. This slide you have all printed out for you already. Covered this last Friday in lab groups, I believe. pHs are going to add up to 14. Here's the equation for calculating the pH if you know the concentration of your hydrogen, or calculating your pOH if you know the concentration of your hydroxide. Those little brackets represent concentrations. So I got 2 of them for you. Lemon juice. Actually, I'll let you work on each of those. Good. So to find the pH. So close to done, but you know what? We're not. We're not done. Not done. So close, but not. The equations that you will have for the test will be, or the equations you should know for the test, are the molarity equations, the dilution equations, and are we given molarity? We're not given molarity and dilutions, are we?
You might get on the half of the pH.
Okay, so we'll probably give you a pH or a concentration equation. So for this one, we're still not quite done.
Guys, almost done.
And honestly, you're not going until you get this anyway. So your pH is equal to the negative log of the concentration. That means the negative pH is going to be equal to the log of the concentration if you type in 0.0032 and hit your log button. That'll give you negative 2.49, which is the negative of your pH, so your pH is actually 2.49. And if you refer back to your pH table, concentration here, still here, concentration of this solution is on the order of 10 to the negative 3, which means your pH should be about 3. Well, it is about 3. It's a little less than 3, and that's because our concentration is a little bit more than just 1 times 10 to the negative 3. Here's the other one. You want to jot it down?
Guys, we'd like to hand in your acid bases 2 up front so they go in the resource room. Many of you already handed it in over the last couple of days. Today.